the rational zero theorem. The rational zero theorem. So let's take a look at that. And once again, you should copy these theorems down in your notes. The rational zero theorem. The rational zero theorem. Now this is a theorem about rational zeros, rational numbers. If you think about rational numbers, a rational number is a number that can be expressed as the ratio of two integers. So these zeros that we're talking about here can be expressed as a ratio of two integers. And once again, the rational numbers are a subset of the real numbers. So if a number is rational, that means that it's real. So the real set of real numbers is a subset of a complex set of complex numbers. So that means that the set of rational numbers is also a subset of the set of complex numbers. Now the rational zero theorem for polynomial functions or polynomial equations states that if R equals P over Q is a rational root or zero of a polynomial equation or polynomial function, in lowest terms. So that means that this fraction here is in lowest terms. Then P, the numerator of this rational root or rational zero, is a factor of the constant term. It is a factor of the constant term. And the constant term, of course, would be the last term to the right in your polynomial function or polynomial equation. And Q, the denominator, is a factor of the leading coefficient. And the leading coefficient is the coefficient of the first term in the polynomial equation. So this theorem here gives you a way of finding all the possible rational roots of a polynomial function or polynomial equation. It's a very important theorem and a very helpful theorem. Once again, the theorem states that if R equals P over Q is a rational root, it states that if R equals P over Q is a rational zero or root of a polynomial equation in lowest terms, that means the P over Q is reduced, the fraction is reduced to lowest terms. P is a factor of the constant term and Q is a factor of the leading coefficient. Now, let's look at an example so that we can see how this theorem is used. As an example, suppose we want to solve this polynomial equation. And this is a very important example because you will have a lot of examples like this to do for your assignment. So suppose we want to solve the polynomial equation x to the fourth plus 2x to the third minus 6x to the second plus 14x minus 7 equals 0. We want to solve that polynomial equation. Now, the first thing we would do in this case is determine all the possible rational roots. And then once we determine all the possible rational roots, we would just use synthetic division to try each one of those rational roots until we come up with the ones that will work. So so we can write down the possible rational roots for the numerator. We know that the roots are the rational roots are in the form r equals p over q, and we know that p is a factor of the constant term. P is a factor of the constant term. So that means that for p possible, we write down the possible factors of the numerator. Possible factors of p. So for p, the constant term here is -7. So we write down the possible factors of -7. We could have 7, we could have 1, we could have -7, or we could have -1. Those are the possible factors for the numerator of any rational root to this polynomial equation. The numerator would have to be 7, 1, -7, or -1, because those are the only factors of the constant term. The constant term is -7. So for p, for the numerator of your rational roots, you have to have the factors of the constant term. Now, for your denominator is the factors of the leading coefficient. The leading coefficient is the coefficient of the first term in the polynomial. So this is the first term in the polynomial, x to the 4th. That means that the leading coefficient is 1. And the factors of 1 are 1 and -1. But here, if we look at this, we've already used positives and negatives in the numerator. If you use positives and negatives in the numerator, then you don't have to use the positives and the negatives in the denominator. You can just use the positives in your denominator if you use both the positives and the negatives in your numerator. So this means that since we've already used positives and negatives here, for the possible factors of the denominator, for the possible factors of the denominator, or for the possible denominators, which is what we really have. For the possible denominators, we would have just 1. That's all we have to worry about, because we have positives and negatives here. If we use +1 and -1, then we're going to get a lot of duplications, and we're going to have to eliminate those duplications eventually always anyway. So this will save us some work later on. Okay, so then we have to write the possible rational roots. So to write the possible rational roots or zeros, you have to take each one of these numerators and put it over the possible denominators. And here we only have one. Sometimes you have several of these possible denominators, several possible numerators. But whatever the case, you have to take each one of your numerators and put it over each one of your denominators, and that will give you all your possible rational roots. And then you have to use synthetic division to figure out which one of those possible rational roots really are rational roots. So that we would have 7 over 1. We put the 7 over 1, we would have 1 over 1. We're just putting each one of these numerators over this denominator. 7 over 1, 1 over 1, -7 over 1, and -1 over 1. And then we reduce those to lowest terms, and we get 7, and we see we have -7, so it would be plus or minus 7, and plus or minus 1, because we have a positive 1 here and we have a -1 there. So these are all the possible rational roots. all the possible rational roots. We don't have any other possible rational roots. So now we just have to use synthetic division and determine which of these rational roots, possible rational roots, really are rational roots. Now, for synthetic division, when we set up the synthetic division problem, the rational roots would go out here. Okay, first we'll try positive 1. And for the synthetic dividend, we just write the coefficients of the original polynomial. We had 1x to the 4th, 2x cubed, then we have minus 6 plus positive 14, and then a negative 7. And that's how we set up the synthetic division problem. We just write the coefficients of the polynomial equation. We bring down the first term, first coefficient, we multiply that times the synthetic divisor, that gives us 1. We add that to the next term, that gives us negative 1. We multiply that times the synthetic divisor, that gives us negative 1. We add that to the next term, we get negative 7. We multiply that times the synthetic divisor, that gives us negative 7. We add that to the next term, that gives us positive 7. We multiply that times the synthetic divisor, and that gives us positive 7, and our remainder is 0. So that means that one of our roots to this polynomial equation is positive 1. That's one of our roots to this polynomial equation. Also in this case, we found out that positive 1 will divide into this again. We bring down the first term using positive 1 again. It turns out that positive 1 is a double root in this case. Positive 1 is a double root. So if we didn't know that, we would just keep on trying all of these and see if any other works. But it does end up that positive 1 is a double root. So we multiply 1 times 1, we get 1. That gives us 0. That gives us 0. We get negative 7. And that gives us that gives us negative 7. And that gives us 0. So we know that this was just the remainder. So you don't use the remainder in your next synthetic division problem. So this is where we would end here. So this gives us a double root for positive 1. So then we tried negative 1 and see if that will divide into the polynomial function. If we tried negative 1, we bring down the 1, that would give us negative 1 here, negative 1, that would give us positive 1. This would give us negative 6, and that would give us a positive 6. The remainder is not 0. So that means that negative 1 is not a factor. It's not a rational root or a rational 0. It means that x minus negative 1 is not a factor of the original polynomial. So therefore we know that 1 is a double root or a root of multiplicity 2. So then we try the other rational roots. We need to try positive 7 and negative 7 to see if they will work. So next we try positive 7. So negative 1 didn't work. So next we try positive 7. We bring down the 1. Positive 7 times 1 is positive 7. That gives us a positive 5. 7 times 5 is 35. Negative 6 plus 35 is 29. 7 times 29, and I have a calculator here that we can use to figure out what that is. 7 times 29 equals 203. 203, and 203 plus 14 is equal to 217, and 7 times that is equal to 15, 19, and we don't have a remainder of 0. So that means that this is not a 0 of the polynomial, and it means that x minus that is not a factor of the polynomial. When we write the factorization here, it tells us that x minus the root, so the root is 1, so we'll have x minus 1 times x minus 1, and then times, so when we did the synthetic division for the first time, we synthetically divided by positive 1, and then we synthetically divided by positive 1 again. Now this last bottom row here will give us the rest of the factorization that we have here. So we have to recall, though, that in the original polynomial, the leading term was x to the 4th power. That's what we had in the original polynomial. So that means that the bottom row here would be 1 degree less than that. This would be x to the 3rd power, and our final row we would have x to the 2nd power. So that means that this is 1x to the 2nd power plus 0x to the 1st power plus negative 7x to the 0 power, which is the same as just plain negative 7. So that means that for the rest of the factorization here, we would have x squared minus 7. So that gives us a partial factorization for our polynomial equation. So now what we need to do is look at this polynomial here. And when we look at that, we see that it cannot be factored using our usual methods of factoring. So now we can just set each factor equal to 0. We get x minus 1 equals 0. That gives us x equals 1. We get x minus 1 equals 0 again. That gives us x equals 1. Here we get x squared minus 7 equals 0. And we can solve this. We get x squared equals positive 7. We take the square root of each side, and we find out that x is equal to plus or minus the square root of 7. So as you can see here, we really only have one rational root, which is 1, and that is a double root, or double 0. So for the zeros, which is the same as the solutions, the zeros are the solutions to the polynomial equation. It's also the roots of the polynomial equation. So for the zeros, we would have 1, and we would have a positive square root of 7 and negative square root of 7. So these are irrational zeros, or irrational roots here, positive 7 and negative 7. 1 is a rational root. So we really have, since this is a 4th degree, since the original equation was a 4th degree equation, we really have 4 roots. So we really need to say here that 1 is a root of multiplicity two. Positive 1 is a root of multiplicity 2. It's what we call a double root. So that's an example of the types of problems that you would have to do on the rational zero theorem.